Good afternoon. Good afternoon and welcome to today's special event, which is the first installation of Science Sundays since 2020. I'm John Beacom, representing physics and astronomy, and I'm the chair of the Science Sundays Committee, which includes people with scientific backgrounds all across the College of Arts and Sciences. As a research leader, Ohio State seeks to expand the boundaries of human knowledge, to understand the implications for our complex society, and to enrich our individual imaginations and our collective culture. As part of sharing the fruits of those research labors, Science Sundays is one of the premier outreach events of the College of Arts and Sciences. Today we're delighted to host Professor Scott Gaudi, my colleague from astronomy. He's the Thomas Jefferson Professor of Discovery and Space Exploration, and he'll be telling us about the search for extrasolar planets and life. Just a couple business remarks. I ask you hold your questions until the end, and then we'll have time for a lot of questions. There'll be a reception afterwards, and when we get up here at the end, I'll tell you where to find the room. And a lot of people have asked, where's the brochure? We're working on a different kind of paper brochure than we used to have. Anyway, let's welcome Scott. Thanks.
Can everyone hear me okay? Yes? All right, thanks, John, and thanks for the invitation. Thanks to all of you for braving the snow to come out to explore strange new worlds with me. So let's get started. As a professional astronomer, there's one question that I get more often than any other question. It's a question that you may have asked any astronomers that you know or asked yourself, and that's, of course, are we alone? Is there life out there? So, you know, there's a fair fraction of people that are very much interested in this question from a philosophical standpoint, and I'm one of those people because I think, you know, we think that the answer to this question, either yes, we are alone or no, we're not, might give us some cosmic context and maybe give us a little piece of the answer to the question of, you know, why are we here? But answering this question is actually quite hard. Searching for life on other planets is actually quite difficult. And so what we do as professional astronomers is we break that question up into more manageable pieces. So the first thing we would want to know is, for example, are there even planets orbiting other stars at all? And then once we determine that there may be planets orbiting other stars, we can ask, do those planetary systems look like our own solar system? And then we can ask, do those solar systems have planets like the Earth, rocky planets with thin atmospheres and liquid water oceans? And if so, do those planets have life? And so we try to answer each one of these questions step by step. Now, answering even the first one of these questions is amazingly hard. Just 30 years ago, we didn't actually know the answer to any of these questions. In fact, for hundreds of years, we only knew of one planetary system, and that's, of course, our own planetary system, which I'm showing here. Of course, I've done some revisionist history and removed Pluto, but this was the one planetary system we knew of, and we thought a lot about how this planetary system, our planetary system, came to be, how it formed, but finding planets around other stars took a long time. And that's because planets are very small in comparison to the size of their parent stars. Now, you might find this kind of hard to believe, considering that we're standing on a planet that is so vast that even though it's a sphere, it looks flat from our perspective. But if you look at the numbers quantitatively, you'll see that planets are quite small. So the size ratio between Jupiter and the Sun is about a factor of 10. So the Sun is 10 times larger than Jupiter. It's about 1,000 times more massive, and it's about 250 million times brighter or more luminous. The Earth, the numbers get even more terrifying. The Earth is about 100 times smaller than the Sun. The Sun is 330,000 times more massive than the Earth, and it's about 10 billion or 1 billion times more luminous than the Earth. So those numbers are very small, and that's the challenge of trying to detect planets. And it wasn't until we started developing the technologies in the late 1980s and early 1990s that we were able to finally detect planets orbiting other stars. And we've developed an arsenal of tools that allow us to detect these other planets. So The simplest one to understand is what we call direct imaging. This is just where you're looking and you see the planet resolved from its parent star. This is actually a planetary system, a famous directly imaged planetary system you're seeing right here over a time lapse, and you can watch the planets as they orbit the star. You can also look for the indirect effect of the planet on the star. So, we were told in grade school that planets orbit stars. That's not true. Planets orbit the center of mass of the planet-star system. And so as the planet orbits around on its circle, the stars are actually orbiting around on smaller circles. And we can look for that wobble either by actually measuring the position of the star on the sky, which we call astrometry, or the motion of the star along our line of sight, which we call radial velocity. And these techniques have been used to detect planets. And then two other techniques that have been successful. One is called the transit technique. This is actually quite simple. If the planetary system happens to have an alignment such that the planet's orbital plane is along your line of sight, once every period of the planet, it will pass in front of a star, cast a shadow onto the star, and the star will get ever so slightly dimmer for a brief period of time. And then the other technique, which I'll talk more about later, is called gravitational microlensing. This is a technique that I've been working on for almost 30 years and helped to develop. And there's an arsenal of other tools as well that enable us to detect planets using a variety of different methods. And so, like I said, in the late 80s, early 90s, we finally developed the technologies that allowed us to be able to detect planets orbiting other stars. And what happened next is actually quite surprising. The first planet discovered around a normal type star, or at least the first one that was really generally agreed upon to be a planet, was the planetary companion to the star 51 Pegasi. So 51 Pegasi is a sun-like star. It's located in the constellation Pegasus. It's reasonably bright, and a pair of astronomers, Michel Mayor and Didier Queloz, were monitoring this star for a period of time, looking for the Doppler shift as the star moves towards us and away from us as the planet orbits the center of mass. And they did indeed find that this star was actually moving in such a way, indicating that there was a Jupiter mass planet with a period of only 5 days around its host star, 51 Peg. And this came as a huge surprise because the giant planets in our solar system are all located in the outskirts of the planetary system. And we came up with very robust theories to explain why that must be true. But then when this planet was discovered, those theories had to be drastically revised. So this was the discovery which won the Nobel Prize a few years ago that really kicked off the field of exoplanets. And now we have, almost 30 years later, we now know of over 5,000 exoplanets. And they've been discovered with a variety of techniques, and they have a bewildering array of properties. So this is a plot that you'll always see in these kinds of exoplanet talks. What you're seeing on the left is you're seeing planet mass as a function of orbital period. And on the right, you're seeing planet radius as a function of orbital period. And each dot represents a known exoplanet, and they're color-coded by the method that was used to discover them. And so we see some very interesting populations of planets. So for example, you see here and here, these are giant planets with radii and masses similar to Jupiter, but located on orbits that are only a few days. Their years are only a few days, like 51 Peg B. And these, like I said, were very much unexpected when planets were first discovered. We see a large population of planets that have mass between the Earth and Neptune. These are planets that have no analogs in our solar system and were also a surprise. It was predicted that there should be a dearth of such planets. In fact, those are the most common planets we know about. We see planets like our Jupiter on long period orbits, and we see features in these distributions. And if we go and we look at each one of these planets in detail, they really do basically have this vast array of properties. So for example, Kelt 9b happens to be my favorite exoplanet, is a planet that is orbiting a star hotter than the sun. And it has an orbit that's only a 1.5 day period. The star is so hot and the planet is so close to the star that the day side temperature of the planet is hotter than most stars. And on the day side, every single element is in gaseous form, including iron and titanium. But then as the material in the atmosphere goes from the hot side to the cold side, those materials condense out and you have titanium and iron rain, which is pretty amazing. There are planets that we think are water worlds covered with global surface oceans. We have planets that are lava worlds, rocky planets located very close to their parent stars such that the rock is actually liquid on the day side of the planet. We have planets that are very, very massive. So Kelt 1b has a mass of 27 times the mass of Jupiter, and its year is only about 30 hours. So this is quite an amazing system. We have super Earths and mini Neptunes, like I talked about. We have systems of 7 planets orbiting very, very low mass stars. Several of these planets are in the habitable zone of their parent star, which we'll talk about, TRAPPIST-1 being the most famous. We have young Jupiters that are still glowing from their residual heat from formation. We have planets orbiting dead stars, white dwarfs, and we have planets orbiting 2 stars, like in Tatooine. So pretty much everything you can imagine and every science fiction planet that has been written about, we've actually discovered an analog to it. So when it comes to that first question, right, are there planets orbiting other stars? The answer is very much yes. And in fact, I would say that Mother Nature is more imaginative than we are when it comes to these kinds of planets. But what about that second question? Well, the second question, we have to use a new technique to be able to answer it. These are the questions whether or not there's solar systems like ours. And we're using a technique that was actually invented by Einstein, although famously, he predicted it would never actually be used to find any planets. It would never actually be observed. And the idea is that if you look at a star for long enough, then another star will pass by your line of sight to that more distant star. So here's us, here's that star you're staring at, here's a foreground star passing in front. That foreground star's gravity will bend the light from that background star, splitting it into multiple images, but also making that star brighter for a short amount of time. And that's the signature of gravitational microlensing. But if that foreground star happens to have a planet, say here, when those images of that background star happen to pass by the planet, you'll see them get momentarily brighter. See it right there. And that momentary brightness, additional brightness, is the signature of a planet orbiting that foreground star. And the nice thing about this technique is that it's sensitive to planets located in the outskirts of their planetary systems, where, for example, the ice and gas giants in our solar system live. And so it's a natural way of trying to look for solar system analogs. And in 2008, a couple years after I arrived at OSU, I led a team of 60 international astronomers where we discovered an analog to our own Jupiter and Saturn using this technique. On the left is the actual data of the brightness of the star as a function of time. On the right shows the properties of this system. The host star has a mass of roughly half the mass of the sun. One of the planets has a mass that's about 3/4 that of Jupiter, located about half the distance of Jupiter from the sun. The other planet has a mass very similar to Saturn, located roughly half the distance of Saturn from the sun. So you have a Jupiter mass planet, half the distance between Jupiter and its host star, a Saturn mass planet, all orbiting a star that's half the mass of the sun. So it's as if you took the Jupiter, Sun, Saturn system and scaled it down by a factor of 2. So we called this a solar system analog, and shows that these kinds of systems do indeed exist. Solar systems like ours, or at least those that have giant planets similar to our own Jupiter and Saturn, do indeed exist. But the true power of this method, the microlensing method, is only going to be realized in about 4 years with the launch of a NASA mission called the Nancy Grace Roman Space Telescope. This is a mission that is going to be the next flagship astrophysics mission after JWST. And it has an aperture of mirror size that's roughly the same size as Hubble. And in fact, the wavelengths that it studies are similar to the wavelengths of Hubble itself. So you might ask yourself, well, why are we launching a satellite that's a mission that's not going to be any different than Hubble? Well, because it's going to have a wide-angle camera lens, essentially. Its field of view is very large, 100 times the field of view of Hubble or even JWST, which means you can survey large regions of the sky very quickly, or smaller but still large regions of the sky over and over and over again. And this telescope will be used to do a variety of things, like it'll study the nature of dark energy and dark matter. But the application that I'm particularly interested in is that it's going to, this is Nancy Grace Roman. She was the first chief in astronomy at NASA and also helped to develop the Hubble Space Telescope. So she's often called the mother of Hubble. So we're very happy to have this telescope be named after such an important figure in US astronomy. But what I'm interested in doing with the Roman Space Telescope is monitoring the very center of our galaxy. The very center of our galaxy, called the galactic bulge, is very crowded. There's lots of stars there. And so in a given sized image, you can monitor the brightness of lots of stars. And so you can look for these very rare microlensing events and then look for planetary perturbations around them. So this just shows a simulation of what Roman might see. You can see in this image about tens of millions of stars. And just to give you a sense of context, this is only about 0.1% of the total survey area that Roman is going to look at towards the bulge. So with this data set, we'll be able to look for these planetary perturbations on these microlensing events. And this shows the region of sensitivity that we predict Roman will have in terms of the planet mass and separation from its parent star. So these blue dots are simulated detections with Roman. And this thick blue curve shows the region of sensitivity. So anything interior to this curve, Roman will be sensitive to. And I'm also showing here the locations of the planets in our solar system on this plot. So there's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you can see that we're sensitive to analogs of all the solar system planets except for Mercury, and even sensitive to planets that have masses of roughly twice the mass of the moon, or roughly the mass of Ganymede or Titan. So we could also detect giant moons. And by combining this with the survey that's already been conducted with the Kepler Space Telescope, which I'll talk about next, we can get a complete statistical census of exoplanets. So at that point, we'll know, at least in a statistical sense, of every kind of planet that's orbiting stars. And that'll really nail down the answer to that second question of, are there solar systems like ours? Right, so in just a few years since the initial discovery of the first exoplanet, we've now answered 2 out of these 4 questions. And what about the third one? Well, detecting Earth analogs is very, very difficult, as I mentioned, because Earth is very small compared to the sun and not very massive compared to the sun. But if you design your mission right, you can actually be sensitive to the signature of an Earth orbiting a sun-like star. And that's what NASA's Kepler mission was designed to do. So it was designed to detect Earth analogs, planets like the Earth orbiting stars like the sun, using the transit technique. That's when the planet passes in front of the star and it creates a shadow. This is a very challenging detection. The Earth passing in front of the sun would create a dip that's only about 1 part in 10,000. It would only last about 10 hours out of the entire year. And the probability that even if there was an Earth-like planet around a given sun-like star, that it would transit is only about 1 in 1,000. So you have to look at thousands of stars continuously on timescales of several years, and you must be able to measure the brightness of all those stars to better than 1 part in 10,000. Sounds extremely challenging, but astronomers like to take on challenges, and that's what Kepler was designed to do, exactly that. And so in the process, Kepler discovered, that's the hardest kind of planet for Kepler to discover, but it was able to discover bigger and shorter period planets very readily. And so it found actually many thousands of such planets. So this is just a subset of the kind of planets it discovered. So this is Jupiter and the sun for reference. That's the shadow of Jupiter on the sun, if you saw it at a distance. And then these are all the planetary systems that were discovered, or some of the planetary systems that were discovered. You can see Kepler discovered planets of varying sizes around stars that are much bigger than the sun, down to stars that were much smaller than the sun. So it really enabled us to detect this large population of planets. And one of the first results coming out of Kepler, the first major result, is that smaller planets are much more common than giant planets. So this plot shows the histogram of the planet sizes of planets detected by Kepler, broken up into different bins. So the Earth, super-Earth, mini-Neptune, large Neptune, and a gas giant. And you can see that the smaller planets with sizes of roughly Neptune and below are much more common than the large planets. And in particular, planets roughly the size of the Earth are actually quite common, as discovered by Kepler. And some of these planets are located in the right distances from their parent star, that if they were rocky and had thin atmospheres, they could actually host liquid water on their surface and thus potentially life. And so these are the Earth analogs that we're looking for. And Kepler and other techniques found a number of candidates of Earth analogs, albeit mostly around stars somewhat smaller than that of the sun. So we know that those kinds of planets are out there. Okay? So we've answered now those first three questions in just the intervening 30 some odd years, less than 30 years since the first discovery of 51 Peg B. We now know planets are very common around other stars, and in fact, pretty much every rock you turn over, you find a planet with a bewildering array of properties. We know that solar systems like ours are probably not rare, but with Roman, we'll really nail down that answer. And we know that Earth-like planets and the rocky planets with thin atmospheres, likely to have thin atmospheres in the habitable zone of their parent star, are also probably not rare either. So what about that last question? What about the search for life? Well, that's a lot harder, as you might imagine. But with these three pieces of information, we can now plan a search to try to find life on planets like the Earth in solar systems like ours. So what's the best place to look for life? Well, a planet like the Earth, right? We know that life arose on the Earth. We don't exactly know why or how, but we know that life arose on the Earth. We know it arose very early in the history of the Earth. So it seems like if we wanted to maximize our chances of finding life, at least life as we know it, we would search for life on planets like the Earth. And so that's, like I said, rocky planets with thin atmospheres located in the habitable zones of their parent stars. And the habitable zones is just the range of distances from their parent star such that the energy they receive from their parent star would keep water to be liquid on the surface. Any closer and the water would turn into vapor. Any further away, the water would be frozen. And water is important because all life on Earth requires water. Right? So this is our goal, is to try to find these planets and then try to see if we can detect evidence of life on these planets. Like I said, this is challenging, but we've sort of simplified the problem into two basic paths by which we can look for life around these planets. And I'll talk about each one of those. One of them is one that we're actually able to access now, and another one is one we're going to be able to access in the future. So I like to think of these two paths as I call them pale blue dots and small black shadows. And so pale blue dots, we're looking for planets like the Earth orbiting stars like the sun. Okay, so roughly, Earth-sized planets located about the same distance from their parent star as the Earth is from the sun. And the other path I call small black shadows. And we study these planets using direct imaging, where we actually resolve the planet from its host star. The second path is small black shadows, and here we're looking for rocky planets in the habitable zones of the parent stars, but the parent stars are much less massive than the sun. We're talking masses about 10% to 50% the mass of the sun. And the technique we use here to detect and characterize these planets is the transit technique. So we're looking for planets that pass in front of their parent stars, and then we can study those planets in detail. And the reasons why we have this dichotomy are due to technical reasons of the kinds of the techniques that we have. Direct imaging works best for planets that are relatively far away, and that's why we want to use this technique to find planets orbiting the sun. The transit technique works best for planets that are orbiting relatively close to their parent star. And for these low mass stars, the distance that you have to be at where you can have the amount of energy you need for liquid water, is much closer. So you can think of this as a very dim campfire that you have to huddle up against to get liquid water. And so these low mass stars, the habitable zones of these low mass stars, are best probed by the transit method. And this is the method that we have at our disposal now. Right? This is the current and near future of the search for life around other planets. So the way this works is when the planet passes in front of the star, the solid part of the planet will just block the light from that star completely. But the light will also from the star will also get filtered through the atmosphere, which is not entirely opaque to the light, but is more opaque at certain wavelengths than others. And those wavelengths correspond to the constituents of the atmosphere. So for example, if you had water vapor in the atmosphere of this planet, then it would absorb infrared light. And so the planet would look a little bit bigger at the wavelengths where water absorbs light. And so by continually monitoring these transits, one after another, as you can see here, we can start to see wavelengths where the planet looks bigger and is absorbing more light, and the atmosphere is absorbing more light. And that way we can look for things like carbon dioxide, water vapor, maybe even ozone, which are signatures of potentially habitable conditions and maybe even life. So we first need to find these planets. We've already found them, as I mentioned, using the Kepler telescope and other surveys. Now we just need to monitor them to look for these signatures in the atmosphere. And the tool we have to do this is JWST, which is 6.5 meter telescope. It's sensitive to infrared light and has exquisite sensitivity and data properties. And so it is our best tool to be able to search for constituent in the atmosphere. And these observations are ongoing. Some of these potentially habitable planets have already been targeted by JWST, will continue to be targeted by JWST. And this is just a simulation of what we might expect from one of these planets, where you might be able to see signatures of carbon dioxide, water, and even methane. So stay tuned. We should get more results from this in the next few years. And maybe if we're lucky, we'll actually detect life on one of these planets, or at least maybe habitable conditions. But of course, these are planets orbiting low mass stars. We're ultimately really interested in planets orbiting the sun, sun-like stars, because they're much more like the Earth. And so that gives us to the future, these pale blue dots. So we would love to be able to get an image like this of an Earth-like planet orbiting another star. It's never going to happen, or at least not anytime soon. You might even hope that we can get this, kind of pixelated, rough image. That's not going to happen anytime soon either. The best we can hope for is this image, which actually shows up even worse on this particular projector than usual. And people, you probably know what this image is. This is the famous pale blue dot image. This little dot there, that's the Earth. So Carl Sagan convinced the Voyager team, as the Voyager 2 was leaving the solar system, to turn the spacecraft back around and point towards the sun to image the Earth. And so at the time this image was created, all life on Earth is located within that one little pixel, this unresolved point of light, blue light. And you might think that, what could you possibly learn from this one little point of light about the planet or even life? And how would you actually go about detecting that? And it's really, really hard. The Earth is about 10 billion times fainter than the sun in the optical, right? And so the analogy people like to use when they talk about this is it's like trying to detect a firefly next to one of those industrial searchlights when the firefly and the searchlight are in Los Angeles and you're standing in New York City. Right? Now that analogy sounds terrifying, right? It sounds like that would be really hard. I was actually curious about that because I'd heard it many times. And I went and I looked up the luminosity of a firefly, how bright a firefly is. I looked up, I combed through owner's manuals of these kind of industrial searchlights that you would see at Hollywood premieres. And I actually found that the firefly is about 1,000 times brighter compared to a searchlight than the Earth is compared to the sun. So the real problem is even 1,000 times harder than that terrifying analogy would imply. So this might think that this is, impossible. How would we ever do this? How would we block the light from the star by 1 part in 10 billion so that we can detect this faint little pale blue dot located right next to that bright star. But we have, over the last few decades, developed the techniques that enable us to do this. And so I'll just show you a couple animations or movies that show how this might work. And so the first technique we have is called coronography. And the basic idea is relatively simple. You just want to put your thumb over the bright star, but not black out the planet light, and then you would see the planet light pass by it. That sounds easy, except light doesn't behave very well. It doesn't behave that nicely, and it's a wave, and so it actually will diffract around your thumb. So you have to do fancy optics to actually correct the wavefront of the light so that you can really just block it out. So here's the idea. There's your coronagraph. It scatters light to the outside, and then you can put what's called a Leo stop to just allow off-axis light to pass through. And ideally, if you did this, then you would see no starlight and just the planet. But because of this wave nature of light, tiny irregularities in your mirrors and your telescope scatter that light, and it's much brighter than the planet. But if you use fancy optics and deformable mirrors to flatten that wavefront, then you can actually effectively block out all the light from the star, and then you can see the light from the planet left over. And so this is challenging for many, many reasons. But like I said, we've been developing the technology to do this. And right now in the lab, we can achieve contrast levels that are about 1 part in 10 to the 9. So we're only about a factor of 10 away from being able to do this to actually detect Earths around sun-like stars. The other technique is one that I actually like a lot. And here the idea is very similar. You're putting your thumb over the star, except in this case, your thumb is a star shade that has basically the size of a baseball diamond flying about 75,000 kilometers away from your telescope. And because the light from that star shade blocks the light from the star, but allows the light from the planet to go by. And because the light from the star never actually enters into your telescope, you don't need all these fancy optics or this fancy telescope to be able to detect that Earth-like planet and to block that light. And so the challenge here, of course, is that you actually have to get this star shade up into space. And you can't just launch something that's the size of a baseball diamond. It has to start off all furled up, and then you unfurl it, and then it goes, and you have to station keep with that star shade such that the star shade is aligned with you and the background star. But again, we've been developing this technology for the last 10 years. Last tens of years. And we now are very close to the place we need to be able to do this, we think. And if we're actually able to block out the light from the star and detect the light from the planet, then what we can do is we can take a spectrum of that planet, just divide the light into its component wavelengths, and we might see something like this. So this is actually a spectrum of the Earth, the actual present-day Earth. And you can see that here, these wavelengths here, for example, the atmosphere is absorbing more light than other wavelengths. And you can see features in here that we can identify as due to water vapor and carbon dioxide and oxygen and ozone and maybe even methane. And that's exciting because we know, so the water vapor is telling us that there's a global liquid water ocean. The carbon dioxide acts as a thermostat on the Earth, so we know it can maintain the temperate temperatures we need to have liquid water. And the oxygen and ozone is a biosignature or biomarker. It's evidence that there's life on the system because all the oxygen on the Earth is created by life. If you just eliminated all the life in the Earth, the oxygen would, after a relatively short amount of time, combine with the materials and you wouldn't see it in the atmosphere anymore. And if you can see oxygen and methane, then that's often considered to be a smoking gun of life. So even though we're just getting this pale blue dot, right, that's 10 billion times fainter than its star, by being able to get a spectrum of that, we can actually see if this planet has potentially habitable conditions and maybe even life. Right? And we've been developing the technologies to do this over the last few decades. We now know that there are planets out there and solar systems out there and planets like the Earth out there. So the time is ripe for us to go and try to make these measurements. And so because of that timing, sometime in 2016, NASA stood up a couple teams to try to study mission concepts that would enable us to block out the light from the star, take a spectrum of that planet, and look for signs of life. And so there were two teams. One was called the Large UV Optical Infrared Telescope team, and the other one was called the Habitable Exoplanet Observatory team. And I was co-chair of this particular team. So these are teams of hundreds of scientists, engineers, people from industry who are all interested in trying to develop these mission concepts. And we spent almost 4 years developing these two mission concepts to exquisite level of detail, such that we had actual parts lists and requirements, and we thought and either we knew how to build it or we knew how to invest the money to go and develop the technologies so that we could build it. These are two very different designs. One is a 4-meter telescope, so not even as big as JWST, and it would use both the coronagraph and the starshade. In this case, the starshade is about 56 meters. And then LUVOIR did not have a starshade, it just used a coronagraph. They considered two designs, a 15-meter telescope and an 8-meter telescope. These are truly enormous telescopes in the case of LUVOIR. And of course, we simulated what we might see with these telescopes. So on the left is a simulated image of the solar system at a distance of 10 parsecs. With the largest of those two telescopes, and you can see Earth, Venus, and Jupiter here. And again, if you took a spectrum of that Earth, then you would see these signatures of habitability and life. This is a simulated image from HabEx of a slightly like a solar system, but a little bit different. And you can see the Earth and Venus, Saturn, and Neptune there. And then this is a dust disk that we put in. So this, we developed these tools to show that we could actually do this with these technologies. And this is, of course, the holy grail. This is what we would hope to get with these two missions. This is a simulated image of the Earth as a function of wavelength. Spectrum of the Earth as a function of wavelength. And you can see these error bars are what the uncertainties we'd expect on these measurements based on the observing time that we had. And we can see clear signatures of water vapor and carbon dioxide, ozone, and oxygen. And all the pieces that we would need to really have a pretty good case that we might be seeing something that's habitable and maybe even inhabited. Now, we don't want to just be able to detect life. We don't want to be able to detect features of spectra of Earth in the present day, because the Earth spectrum looked very different in the past. Right? So these are simulated spectrum of the Earth in 3 different epochs: Archean, Proterozoic, and modern Earth. This is the one I've been showing you already. But if you look at Proterozoic Earth and Archean Earth, where we knew there was life, the spectra look very different. And in particular, for the early Proterozoic Earth, there's very little evidence of oxygen, although there's still evidence of ozone. And in the Archean Earth, you start to see things like photochemical hazes as well. So we need to be able to detect those kinds of features and really know that those are due to life and habitable conditions as well. So, of course, we don't want to do this for one planet. We want to do this for as many as we can, because we don't know if every single planet that's rocky with a thin atmosphere in the habitable zone is going to have liquid water and maybe life. So we want to get a sample of these systems. So these two plots show for the two different telescope architectures, 2 different studies, the number of planets we would be able to detect and characterize as a function of the size of the planet here and the temperature in the colors, so hot, warm, and cold. And then the green bar is analogs to the Earth. So with HabEx, we would detect only 8 analogs to the Earth, we think, and that's folding in astrophysical uncertainties. For LUVOIR, it'd be more like 50. Right? So that's kind of brackets the range of possible missions that we can envision building that are still able to address this science. So, like I said, these studies took about 4 years. We developed these very sophisticated mission concepts. Now what? Are we going to do these missions or not? So I have to explain why we are going to do these missions, or one of them. I have to tell you exactly how missions get launched and built in US astronomy. So every 10 years, astronomers in the US get together and they appoint a panel of roughly 20 of their best and brightest and smartest astronomers that become the Decadal Survey panel. And then the astronomical community gives that panel a bunch of input as to what they think we should be spending our money on in astronomy over the next 10 years. The panel collates that input with the help of many other panels as well, collates that input and comes up with a recommendation for what the future, the next 10 years of astronomy should look like. And this is called the Decadal Survey, and this has been going on since 1970. And each Decadal Survey made many recommendations, but they each recommended a large flagship mission for NASA astrophysics, space mission. And so you can see, and these are the origins of missions like Hubble, Chandra, Spitzer, JWST, the Roman Space Telescope. And so, those of us that worked on these mission concepts, we submitted these mission concepts to the 2020 Decadal Survey, which got a little bit delayed because of the pandemic, so it was ultimately the 2021 Decadal Survey. We submitted to them, we presented our concepts to the panels and said, this is what we think it can do, and we wrote very long 500 to 1,000 page reports detailing all the work we'd done and trying to justify our claims. And they took and they ingested that information. And actually, there were two other mission concepts that weren't focused on the search for life as well. And they also made presentations. And so the Decadal Survey could have chosen that to prioritize none of these missions, or prioritize one of these missions, or prioritize all of these missions. And in fact, and so the report came out in late 2021. It was a very ambitious and inspirational report. I do want to mention that I think it's very important. This was the first Decadal Survey report that made recommendations about the state of the profession, about the culture of inclusiveness, diversity, and equity, and also made recommendations that those efforts should be funded. So I think that's an important step forward for our field. But their recommendation for the first large mission concept is shown in this paragraph. So I just read it for you. Inspired by the vision of searching for signatures of life on planets outside the solar system and by the transformative ability of such a telescope would have for a wide range of astrophysics, the survey recommends that the first mission to enter this program is a large 6-meter infrared optical UV space telescope. And the goal of this mission would be to try to detect potentially habitable planets and even evidence of life. So they recommended that this is, and notice the words, the first mission. They actually prioritized all of the missions. Well, they prioritized 3 missions, and then they combined the Habex and LUVOIR mission into one. So this is a very ambitious survey that would answer some of the most profound questions we have in astrophysics, not just are we alone, but how do galaxies form and evolve? How do planetary systems form, et cetera? And so, and these recommendations for this Decadal Survey are taken very seriously by the agencies that fund science. And in particular, in this case, NASA takes these very seriously. So this was the next mission after the Roman Space Telescope that the Decadal Survey prioritized. NASA has taken the first steps to start developing this mission, which one of the first things they did was they renamed it the Habitable Worlds Observatory. And I was just at a meeting in Seattle at the American Astronomical Society meeting where a bunch of us were discussing the process of how we were going to start to develop this mission concept based on the information that we had from the LUVOIR and Habex mission concepts and move forward. And this requires, developing the mission, the specific design of the mission. It requires developing technologies. And so the next mission in this survey in this series is going to be the Habitable Worlds Observatory. Of course, it's also going to require money, right? And let's just be realistic about this. So this is what we call a sand chart. Shows the budget of NASA astrophysics as a function of year. And then these different slivers are different lines that the funding goes to. So this is sort of like research and analysis. These are smaller missions, Explorers and Probe. Here's JWST. You can see the amount that it costs. This is the Roman Space Telescope. And this is a projection of how much the Habitable Worlds Observatory and then the other two telescopes would cost, assuming a launch date of 2041, 2047, and 2051. And so this is where we are now. And you can see that we would have to increase the budget of NASA astrophysics by about 30%, or about $500 million per year, by $500 million per year, which really does seem like a lot. Okay? And this would require the astronomers, stakeholders, Congress people, and you to actually agree that this is something we want to do, right? This is ultimately coming from taxpayer money. And so it seems like a lot of money, right? $500 million seems like a lot. Well, just to give you a reference, this is about, that line up there is about 50% of what Americans spend on potato chips every year. So, you can either have that, or you could have that, and still have quite a bit more potato chips. So, joking, of course, but the point is that this is within our capability to do this, right? We now have the scientific knowledge to know that the planets exist, solar systems like ours exist, Earth-like planets exist. We developed the technologies to be able to block out the starlight, to detect these pale blue dots, take their spectra, look for habitable conditions, look for life, right? We're there, we can do this, right? And not maybe next year, but within the next few decades, right? But it just requires the collective vision of everyone that is part of this endeavor. And it's not just astronomers like me. It's also Congress. It's also OMB, the Office of Management and Budget. It's the president, and it's the taxpayers, and it's you in this room that have to get behind this vision of being able to go out there and try to answer one of humanity's most profound and enduring questions. Right? So if you take anything away from this, I want you to take two things away. One, we're in this very special time in human history where we really can go out and try to answer this question, or at least start to answer this question. And two, these telescopes are not telescopes for astronomers or NASA. These are telescopes for the people, and they're your telescopes. So I was part of a National Academy of Sciences Exoplanet Science Strategy Report. I co-chaired it with my fellow colleague, Dave Charbonneau. And we laid out a strategy for exoplanets over the next 10 years. This was before the last decadal survey. And so it was very influential in the decadal survey. And so, we said, I want to leave you with a couple of quotes from that. One is that the search for life on other worlds is both a profound and profoundly difficult endeavor. I like that quote. I like this one better, partially because I wrote it. For generations, humans have looked up at the stars and wondered whether we are alone. Wonder at this very question unites us. It is unknown whether this generation will be the first to learn that life is common throughout the galaxy, or the first to discern hints of cosmic lonesomeness. What we do know is that we can be the first with the technology and scientific ability to answer this question if we so choose. Thank you.
Thanks, that was great. That was great, thanks. Okay, we have time for some questions. We can turn the house lights back up. So go ahead, just shout it out, and then if it's not loud enough, I'll repeat it for you.
How much cooperation or lack of it do you get from the rest of the world?
So I'll repeat that, or go ahead.
So how much cooperation or lack of it do we get from the rest of the world? So these missions the NASA astrophysics missions have grown to the point where they're really no longer really able to be contained with just one country. And so it really will require, input and money and resources from the world to do this right. And I will say that, we have a very strong heritage of doing this. So James Webb Space Telescope is a joint venture from US, Canadian, and European astronomers. Hubble Space Telescope had international cooperation. We're cooperating with Japan, Europe, and I'm blanking on who else, with the Roman Space Telescope. So yeah, this is definitely going to involve cooperation from other agencies in other countries.
Let's go over here first. And then.
Yeah, so based on all the knowledge that we know about potential aliens out there. If you think 50% being unsure at all, zero meaning you don't think there is, and 100% you're absolutely certain, what's your gauge?
All right.
Summarize
So,
the question.
on a scale from 0 to 100%, how sure am I that there's life out there? Is that basically a good rephrasing of your question? You're not going to like my answer. My answer is I'm a scientist, so I have to say I don't know. And actually, I don't have any more information on this than you do. I can give you what I do know. I do know that life on Earth arose almost as soon as it could. It actually arose, it might have even arisen multiple times and then got wiped out. So that seems to suggest life is pretty robust, right? That sounds good. And like I said, and I've given you the information about how common planets like the Earth are. Water is very common. Rocky planets seem to be quite common. So, I think I personally kind of ascribe to the principle that we're not particularly special. So I would say that I would guess that simple life is probably pretty common. Intelligent life is an entirely different question, and I won't address that. But I really just don't know. That's why we should go out and do it.
Go ahead. Did you have a question?
Some of these planets in the Goldilocks zone, some of the closer ones, how long would it take us to travel there at our current technology?
Oh God.
Just summarize it.
Yeah. So how long would it take us to get to some of these potentially habitable planets with our current technology? I actually don't know the answer to this question numerically, but the closest planet that we know of that is maybe in the habitable zone of its parent star is an Earth mass planet orbiting Proxima Centauri b, which is the closest star to the solar system. It's not quite in the habitable zone, but it's close. But that's with our current technology, it would take, I don't know. Does anyone else know the answer to this question?
Guesstimates.
I think it's
hundreds of years. I mean, some order a few light years, and we can go
right.
1%.
1% the speed of light, right?
Yeah. 200 years?
A few hundred years.
Front row.
So to go forward with these future projects or missions, you needed more budget. It would appear. What strategy are you undertaking to increase the budget when probably the layperson would prefer his potato chips over? I mean, in all seriousness.
No pun intended. Layperson. Yeah.
Oh,
So what?
Oh yes.
What strategy do I have for increasing the NASA astrophysics budget? Given that the average person probably would rather have their potato chips. I don't know that I agree with that last part, right? I think if you asked the people, would you be willing, and you don't have to give up all your potato chips, just half of them, right? If I asked the average person, were you willing to give up half your potato chips every year to do this? I think a lot of people would be down for that. But that's not really, it's a false choice, right? That's not really the question. The thing is that the strategies are, one, giving talks to kind people like you, so that you can write your Congress people and tell them that this is a good thing to do, that we should be doing these kinds of things. But also, I expect to be spending a fair amount of time on Capitol Hill talking to my Congress people as well. And I go around giving talks to various audiences. Whoever will listen to me, I will talk to them about this. And I'm obviously not the only one doing this. There's armies of people that want to get involved with this.
Let's see. A lot of questions. Go ahead.
So you're focusing on planets where life would look a lot the way it does here.
Mm.
I remember reading a science fiction story many years ago about somebody from another planet where instead of carbon, things were built on whatever's the next one up on the
Second one down, silicon. Right.
and then it wouldn't be water, it would be some other compound.
Yeah.
It's science fiction, but is there any plausibility in that sort of thing?
Yeah. So is there a plausibility? Is it possible that life may not look like life as we know it? I think is a fair summary of your question. Sure, of course. This is not my field, so I'll just say that right off. I can tell you something about silicon life, right? So we're a carbon-based life form that uses water as a solvent. Okay, why water? Well, water. If you take the two most abundant elements in the universe that actually like to play well with other elements, those are hydrogen and oxygen, form water. Okay, so this water is just very abundant. It is liquid over a very large range of temperatures. It's liquid over a range of temperatures where lots of chemical reactions are reasonably fast. And so it's good for that. Carbon has lots of great properties. It forms double bonds, it forms these rings, it does a lot of things that are really important for life. If you ask silicon, silicon doesn't form double bonds with itself. So it makes it less good as a structural component. If you mix silicon with the most abundant element in the universe that's not hydrogen, that likes to combine with other elements, oxygen, you get silicon dioxide, which is sand. Not very useful for life. So there's reasons why silicon life is challenging, I think. And similarly, you can make similar arguments for using ammonia as a solvent or methane as a solvent at liquid temperatures. They're liquid at a narrow range of temperatures where it's much colder, chemical reactions are slower. So I think there's maybe a very good reasons why nature chose carbon-based life with water solvent. That said, why are we focusing on that? Well, those are reasonable reasons, but the truth is, this is something we know what to look for. We know how to look for this. If you just said, I don't want you to design a mission to find life as we don't know it, I would have no idea what to do. So start with something you know.
All right, let's take two more questions up the middle here, and then we'll go to the reception. Go ahead.
So I have a question. So we know geothermal can support life. So could it be possible for a planet that is very far away from the actual habitable zone, but with enough geothermal activity could sustain life?
Yes, that's a great question. So could you use geothermal energy to maintain liquid water on the surface of a planet or interior to the planet, even when you're not in the habitable zone? Yes, that's possible. You also have radioactive heating as well, can keep you warm for a while. And so, if you ask me what the most likely place in the solar system for there to be life, I would say Europa, which is not in the habitable zone, but is being kept warm to tidal forcing from Jupiter and has a subsurface liquid water ocean and almost certainly underwater thermal vents, which we think all life on Earth may have arisen in these underwater thermal vents on the Earth. So yeah, it's a challenge to try to find life on those systems because like Europa, if we tried to look at Europa from 10 parsec or several light years away, there's really no way we would know that it has life. We can't even figure it out if it has life from our vantage point. So.
Okay, last question, sir, with the scarf.
This question is a little bit closer to life on campus. What do graduate students do these days with all the data and things and uncertainties?
I don't know. I think they have the time of their lives, I guess. I mean, this is a great time to be a graduate student in astronomy, right? Especially with JWST, just bringing back amazing amounts of data. So yeah, I mean, there's a lot to be done. So.
Do they know what data they're going to get?
Well, sometimes they apply for it and get time. Sometimes they just use data that's publicly available. Right? It just kind of depends on the topic. Some graduate students obviously don't use data at all. They're just theorists. So. But it's a great time to be an astronomer, I think.
Okay. So let's.
Have we looked at like moons of the super planets to see if they can sustain life?
Well, so I mentioned Europa, and Enceladus is a moon of Saturn that might have a subsurface ocean or pockets of ocean. If you wanted to detect moons around planets around other stars, planets orbiting other stars, that's really hard, but we're just on the cusp of being able to do that using a couple different techniques. I think it would be really hard to determine whether or not they're potentially habitable, though.
Okay. I'd like to thank everybody for coming back to Science Sundays, which will be resuming this spring. And I'd like... It's great to see a lot of familiar faces from the 2020 series and earlier, and I hope to see more. Start bringing your friends again. And we'll go now to the reception, which will be in the Great Hall. It's on this floor. Basically, go out and go to the right, towards the front of the building, and to the left. And there's coffee and cookies and other snacks. And also, you'll have a chance to talk to Dr. Gaudi. It's more. So thanks very much for coming, and see you next time.